All right, howdy. So what we'd like to do is we'd like to get into fields from charged objects. So we want to see what happens with those. The main thing that we're going to do in this first part is we're going to talk about what happens from a charged sphere. This is pretty important. This is what gives us the main result for the force, how people usually talk about the force between two objects, which is that if you have a charged particle here and a charged particle here, then one of these guys will be producing a force, or actually they'll each be producing a force on the other one. So that if I'm looking at the point of view of this guy will be producing an electric field coming out radially from the center here. And that's what I'm going to talk about in just a moment. And this guy will get a force from that. So if this guy is also positively charged, remember the whole thing about like charges repel and opposite charges attract. What's going to happen here is this guy's going to get pushed this way. Right? He'll have a force in the opposite direction. But if this has a negative charge, then he'll feel a force this way back in towards him. And of course you could reverse the idea, right? So if this is happening here, then this charged object is making a charge or a field from that guy, and this guy is also making a field, and because he's negative, his field is in the opposite direction. Negative fields go into negatively charged objects and out of positively charged objects. So this guy's a positively charged object. He's got a field that's going this way, so his force is coming in. Right? So he's putting out a force this way. This is negatively charged, so it goes in the opposite direction of the field, so it goes towards this guy, and the opposite down here. Okay, so that's basically what we call Coulomb's law. And maybe I'll make a video talking about how Coulomb did that. Maybe, maybe not. I mean, it's a fairly interesting result and obvious. And also, it's the sort of paradigmatic experiment that allowed Cavendish to do a similar experiment on gravity to figure out how much the Earth weighed. Right? So that's a very interesting experiment. And you may remember this says that the force is equal to this Ke. This is called Coulomb's constant. Which we defined last time, times the product of these charges over the square of the distance between them. Okay? And that's the distance between their centers. So it's this distance here is r, or little r, and I have to write it in the backwards direction. So that's little r, and it's not this distance here, which is technically the distance between them, because this is the distance between the surfaces. It's the distance between the centers, this r, that the field produces, no matter what the charge distribution inside, kind of, as long as it's uniform, right? As long as it's radially the same. So it doesn't matter if it's all in the shell or if it's a completely uniformly charged sphere, it's going to be the same. Now, if you get funny objects, different things happen. We'll talk about funny objects a little bit later, all right? But that's the main idea behind Coulomb's law and what happens. And if we look at this, we can see how the field is coming out of that, right? So we're looking at the force on this Q here, and that force from that Q is still Q times E. The force on Q is Q times E, so this part here is the electric field, all right? So if that's the electric field, that's what we want to find out about the electric field, and then later on, if we have multiple things like that, if we have multiple sources, then we can add them up. In fact, this is how most numerical work is done if you want to calculate the field from a funny looking object, right? You'd figure out what the force distribution is, throw it into a computer, and the computer will add up all the little charges, basically. It's a little more complicated, but not that much more complicated. That's the basic idea. There's a slicker way to do it, but it only works for really, really symmetric situations, like the force from a sphere. And that's what we care about today, is just the force from a sphere. So a charged sphere produces an inverse square field. Just like gravity, right? This looks very much like Newton's law of universal gravitation. So E is equal to KEQ over R squared, and it's going out from the center. That's the direction. Now that's the exterior force. On the inside, that can be different things. The interior force depends on the distribution. Interior field, force. So, depending on what the distribution is, it can be almost anything. But probably one of the two things. If the charge is all on the edge, like it is in a metal, then actually what happens is there's no field on the inside. It's really awesome. There's no field on the inside. You can sort of see that. There's no reason for it to be different on the inside. If it's completely uniform, if everywhere in that sphere you have the same amount of charge, if, say, every atom lost an electron, which would be a really huge charge, that's not going to happen. But if something like that happened, then what you'd have is you'd have an increasing field from 0 at the center. It has to be 0 at the center, because by symmetry, if everything is radially symmetric, if everything's symmetric as far as spinning the object, then there's no difference between any of those directions. So it has to be 0. So it'll be 0, and it'll go up to basically this value at the edge, where this little r is going to then be the radius of the sphere. And it has to match at that radius in that case. So if there's no surface charge, then the field at the edge and the field on the inside have to match. So that is more or less what happens. We will not be dealing with interior fields in this class. There are a lot of interesting things that happen with them, and they might be interesting for some technical applications. I'm not sure. I haven't actually seen those technical applications, but they are pretty good for the sort of thing that we're doing in this. But they aren't really good for what we're doing in this class. What we care about is the forces from individual charges, all right? So I think that's probably all we need for this. I'll do some calculations of this type in the example.